If you're following the IoT show, you certainly know what tinyML is about, and you've heard about Edge AI in general. I think it's time we do a myth and reality episode with someone who is very much into tinyML. Dan, who is Director of Machine Learning at Edge Impulse, is joining me to discuss where you can find Edge AI and also discuss the realities, what is possible, what is not, as well as what's to be expected for Edge AI in the next 5 years. Hey everyone, this is the IoT Show. I'm Olivier, your host. We have Dan from Edge Impulse today to discuss myth and reality of Edge AI. Dan, thanks for joining us today. How are you?
Hey, I'm really good. Thanks. And thank you for having me on the podcast.
Fantastic. So I like to ask people, where are they calling from? Where do you live?
So I'm in Charleston, South Carolina. It's on the US East Coast. We have palm trees and alligators.
In that order. In that order.
I see them
Awesome.
every time I go out for a run.
And that's why you run? Because of
Yeah,
the
through the
alligators?
swamp with the gators.
That's a good motivation. I like that. I like that. So then tell us about yourself. Who are you? And tell us a little bit about Edge Impulse as well, which is the company you are with.
Yeah, cool. So I'm the director of machine learning at Edge Impulse, and we're a startup that builds tools that makes it much simpler and easier to develop machine learning algorithms for edge devices and for edge applications. So I have a really kind of random background in technology. I've done pretty much everything from web engineering through to machine learning. But for some reason throughout my career, there's been this kind of gradual gravitational pull that's pulled me towards AI and machine learning and building stuff for the edge. And so I'm really living my dream life at the moment with the stuff that I'm doing. It's it's this moment in time where the two things that I am most fascinated by, which is like hardware and machine learning and AI, have come together.
Yeah. I understand you because I've been in the IoT space for, ever. And this combination of hardware and software, and now AI coming on top, which is like evolution of software and hardware combined together. And yes, I hear you. Like we're living the dream, right? And it's ours. So that's pretty cool. I love that. So Dan, you guys, you're modest because Edge Impulse is not just yet another Edge AI solution. It's actually, from my perspective, was one of the best, if not the best, if not the only solution you would want to use these days to run AI model on tinier devices, on microcontrollers and so on. And this is not an easy fit because we're talking about running things that have been designed or thought for having infinite resource and in terms of memory and compute and so on. And you guys have decided, no, wait a second, actually, we're going to need to distribute that intelligence all the way down to the edge to devices. And for that, we need some tools. And so Edge Impulse is not recent. Like you guys have been working on that for some time already. But tell me a bit more about, the inception of Edge Impulse in the context of what's happening with AI at the edge.
Yeah, absolutely. So really, the story of Edge Impulse is starting around 4 or 5 years ago. The company's about 4 years old. I've been there since the beginning. I joined just when the founders were looking for their first hire, and I joined the company from Google. And what I was doing at Google is working on a product called TensorFlow Lite for microcontrollers, which is basically a tool for taking TensorFlow deep learning models and deploying them to embedded devices.
Mm-hmm.
And at the time, that was super new. No one had really thought about doing this before. And if you had to do it, it was really, really manual. You had to write your own C++ implementation of all of the layers of the model and figure all of the optimizations out for yourself. So TensorFlow Lite for microcontrollers was like this step in the right direction for making it easier for people to bring models that were trained on GPUs and bigger machines and run them on constrained devices at the edge where things like optimization are super important. So while I was at Google, um, Pete Warden and I, who Pete's the guy who came up with the whole idea of TensorFlow Lite for microcontrollers, we wrote a book together about how to start training models and deploying them to embedded devices, mid-range microcontrollers kind of thing. And we ended up writing this book called tinyML. It's about this
Yeah,
thick. It's sort of like almost everything you need to know to get
it's
started
like
doing this stuff.
tinyML in a not tiny book, right?
Yeah, exactly. And it's crazy because I had this experience where I knew Zach, who's one of the founders of Edge Impulse, because he was working at ARM on the time, and working on some similar projects. And we met through some collaboration we were doing between ARM and Google. But then Zach quit ARM, and then at the tinyML meetup, which I was running at the time in Silicon Valley, Zach came and presented this product, which was the prototype of Edge Impulse, and in a couple of minutes of presentation, made our entire book obsolete. So it was like, wow, oh my god, this stuff really can be quite easy if the tooling exists and if it's designed in the right way. So that's been the goal of the company, really, is to distill what you would previously need some big thick books. Subsequently, Jenny, who's one of my colleagues at Edge Impulse, and I wrote another book about embedded machine learning called AI at the Edge. That's also really thick. Our goal with Edge Impulse is that you should be able to participate in this world and use these tools and build amazing things without having to read these huge thick books. Uh,
Yeah.
it's a journey. We're evolving with the industry and with the use cases and applications that are coming up, but we're gradually getting there. And there are just so many different obstacles and barriers that are in people's way if you're trying to do everything yourself. It's
Mhm.
almost believable. The tooling, the difficulty getting the tooling to work together, the domain expertise that you need, and ideally someone who has domain knowledge about a subject area. So if you're building an application for healthcare, you should have domain knowledge about healthcare. You shouldn't need to have all this deep knowledge about embedded
Yep.
engineering, deep learning, machine learning workflow, all of that stuff. There should be tooling available that helps you with that. So that's our goal. That's what we're trying to make possible.
I like that. And vice versa, by the way, right? If you are in data science or software development and you're developing a medical device, like to
Mhm.
just give the example, you shouldn't have to be an expert in medical, jargon and whatever. And so actually there's an exercise that Edge Impulse I think is doing really well, which is abstracting complexity, something that at the end of the day is not so hard. You implement the complexity, you expose APIs, tools, whatever. Too often I'm seeing an abstraction layers abstracting too much, becoming black box that you can't control, can't configure, whatnot. I think Ed, from my perspective, I'm newbie, know nothing about neural network and AI and so on. When I first played around with Edge Impulse, it made sense. It was logical for my embedded developer brain, and it was easy to use and comprehend because you're not hiding the concepts. You're making them simpler to work with. From my perspective at least. And so I think that's one of the things that Edge and Pulse is doing really well. So we'll see that in action in a little. So we'll dive deeper. But before that, I would like for you. The title of the show is Myth and Reality about Edge AI. Let's take a look at the realistic and unrealistic expectations with Edge AI. We're talking about limited resource. We say that constrained devices, right? So that means you have limited memory, limited compute. Edge and Pulse is doing a lot of optimization, but what are the things that you can really expect from embedded and constrained devices technology today in order to run AI on?
Well, this is a great question, and it's actually something that's changing all the time. So, when we started, the question was how can we run models on these basically like mid range microcontrollers, Cortex M4 type stuff, to do some basic things. And then, as the time has gone on, and companies have realized that there's actually so much you can do on the edge, that we need some really really beefy compute on the edge that's still energy efficient. The scope has grown and grown and grown to the point that things that were not really feasible at the beginning are now feasible even with low power. So it's really a cool time to be getting into this field because we have such a range going from these kind of low and mid-range microcontrollers running simple models doing things like time series analysis, understanding audio, doing things like keyword spotting or audio event detection, or identifying events in time series data, going through to some simple vision. So having a couple of frames per second performance, like a few frames per second for image classification or object detection, which is where you're like finding objects in an image and drawing little boxes around them. And then you start to get into the accelerators, NPUs, which are neural processing units, and these are chips that are specifically designed to run deep learning algorithms. So
Mhm.
they give you, for the same energy budget, potentially an order of magnitude or more performance. And so you can then start to do real time or close to real time vision, image classification, and object detection on these tiny constrained devices that have very, very low energy consumption. You can do real time, audio with pretty high resolution. Um, you can run multiple models at the same time on the same device. You can run a model alongside all sorts of application level logic that's happening as well. And you have to um, remember that it's not just the model that's running on the devices. There's an application that has to coexist with it.
Yep.
So you can have things like co-processors or multiple cores, which allow you to have your machine learning inference happening on one core and your application running on another. So the other thing that's changed is that devices have started to get more memory, more ROM to fit the weights of the models, and then RAM
Mhm.
to fit the model's activations during inference. And so that's been growing. And we're also seeing improvements in algorithms. So, algorithms that are more efficient, that have been designed specifically with these types of targets in mind. But then the next thing that's happening is that we're getting even more powerful hardware at the edge, that is equivalent to the type of power that you can get on like desktop computer GPUs. And so we've got these um, there's like NVIDIA products, for example, the Jetson
Mhm.
Orin products, which are full beefy GPUs, but designed for use at the edge. They're not going to be, running for months and months on a coin cell battery like some of the smaller devices. But sometimes if you're in an industrial setting, energy isn't as much of a concern, but you want to have super low latency. So maybe you've got like a dozen cameras observing a production line, looking out for faults and issues. And you can have all of those feeds coming into this one device, and it's running a whole bunch of different models at the same time, detecting all sorts of different things across all these different cameras. And then the very kind of large edge, you have these edge servers, which are basically like big beefy data center
Yep.
servers that happen to be living at the edge, and you can do all sorts of crazy stuff there. Analyzing these big streams of video, sensor fusion across all these different simultaneous feeds of data. So it's really a huge range. And we've gone from just focusing on the smallest stuff through to, okay, now you can replicate everything you can do in the data center and on the server, but you have all the benefits of low latency, incredible reliability, that you have on the edge. So
Yep.
then it goes the whole way from like wearables and gadgets and smart devices through to super hardcore industrial application. If you think about like a self-driving car, that is an edge AI device, right?
Mhm.
It's like the sort of biggest IoT device. Actually, maybe the biggest IoT device would be like a self-driving container ship, which exists, right?
Yeah, totally. I hopefully they don't hit a bridge, but right. Too soon. Too soon. I'm sorry. I'm sorry. But yeah, there's lots to unpack from like everything you say. I think the main things I want to call out, especially for our audience here, is that when we say edge AI, it's not one edge device. It's actually in a distributed system. And what's recent or new, well, the hardware is being becoming better and better at the various, sizes of the edge of embedded devices all the way up to the on-premise servers. And now you need to think about how you're going to distribute that intelligence. And as you were saying, low latency is critical. And what's to me really new is the fact that you can start running things that go beyond just detecting, a threshold that's been reached on a sensor. You can now do things as smart as anomaly detection on something that is super tiny, running on battery, and is specialized. I think in the world of embedded and IoT, you need to think about specialization. Each entity will do a job, right? I think robotics is a fantastic example of, different parts of the brain working together, whether it's a swarm of bots, whether it's an entire, factory floor that is automated. And it's all about identifying where you can bring that intelligence and dispatch it so that it's the most efficient for what you're looking for. And edge impulse and this kind of solutions that are looking at enabling tinyML, they're bringing that capability of not having just one big brain, but dispatching that intelligence for optimizing latency, privacy and security, safety, all these aspects that are needed and required. One aspect you didn't mention, one of the big powers, especially of big models and AI systems, is continuous learning systems that are able to correct or optimize the algorithms, the models as they go, right? And so until now, you'll tell me if I'm wrong or not. When it comes to edge AI, especially tinyML, the models are already at capacity of what the hardware can provide. Even though hardware is going up, BOMs for embedded devices are limiting what you can do. So you have to find the right balance between the hardware and the scenario you need to implement. And so these systems, are they able or will they be able to start doing continuous learning even if there are these tiny devices down there, or will you still need to rely on training in the cloud where you have all the GPUs and so on that are necessary to do training of models?
Yeah, so it's a really interesting thing. I mean, I think technology wise, we have devices that are powerful enough to do some training and customization on device already. And it doesn't have to be super complex, full um, deep learning happening on a microcontroller, but are ways that you can basically understand the distribution of what you're seeing as inputs and then gradually adjust to that. If you're doing anomaly detection, for example, you can learn a baseline and then start to notify the application if there's something that's happening that goes outside of that baseline, using some
Mhm.
fairly simple algorithms. But one of the challenges here is that we aren't just constrained by hardware capabilities and by technology. One of the basic constraints is around data and labels. And one of the things that it's nice to think we could deploy this magic box into the field and it can just learn things as it goes along, like a baby learning about the world as it interacts with things. But what we actually need isn't just a baby out there in the world by itself, but it always has a teacher and a parent and um, things to guide it. And it's the same with machine learning and AI. You can't just get something from nothing. And so a big challenge we see is that in order for the model to learn something reasonable, it has to have labels that tell it what is going on in the world. So if you have um, some items coming down through a production line and you want to train a model to understand which ones are perfectly manufactured and which ones have a fault or a defect, you need to have some data that shows what the perfect ones look like in order for the model to be able to discern between them. And if you
Mhm.
put the model out there just in the field to learn, it has no way of discerning between those things by itself. So if you happen to get a run of defects and the model's in this kind of learning mode, maybe it will learn that the defects are normal. So that's just one example, but this applies for everything. You can't often just do this kind of unsupervised approach, we call it, where you're just letting the model pick things up from its training data. for most applications, you also need a source of labels. So the key becomes, how do you design a system that allows you to get those labels in? And maybe it means collecting a bit of data. One thing we see is very powerful way of doing this is to have a sort of staged deployment. So your first few devices you deploy out into the field, and you have kind of a human in the loop. You collect data and you see what the results the model is giving you are, and then a person can help validate those and make sure that they're correct. And then any data you collect can go back into training, and you go through this period of time where you're doing this more intense kind of human involved data collection and labeling that's assisted by the model. And then once you've got confidence that it's working in the real world, you can go out and do more. So there are also systems where you can use bigger models to help label your data. So we allow that in Edge Impulse. So you can collect a bunch of data. Collecting data is easy. Well, sometimes collecting data is less expensive than labeling data, because
Hmm.
labeling involves applying some human expertise a lot of the time, which is
Yeah.
expensive. So if you can use a big, super capable model, like even some of these newer generative AI and foundation models, to help label your data, because those models are so much more capable than the little tiny models we can deploy to the edge, you can use them to label the data and then train a model for the edge using that labeled data. And it's still probably not going to be as good as if a human looks at the data and labeled it, but it's a lot cheaper. So it's all about understanding the design tolerances that you're building towards, and where can you um, make the most of the resources you have.
You just debunked a myth here where everyone is freaking out that AI is gonna replace people's jobs and so on. I always tell like everyone, like, don't freak out. It's gonna change the way you're working, but humans are necessary and can still do things that many devices can't. And man, even like when these machines will be smart enough to match what we're doing, we're still the creative, the instinctive brain that these things will not be for some time. So we're safe there. So thanks for saying that, hey, these models will be intelligent because humans are, and so they need to stay like that. And there's also a domain expertise required, right? So people will not become dumb; they will still be experts in their domains because that's necessary to configure and train these models. So that's nice myth you just debunked here.
Yeah, absolutely. And to kind of dwell on the domain expertise, the way I think of machine learning, the whole point of it is to capture domain expertise from people and then push it into this software programs that you can then deploy to places where it's difficult for people to go. So the whole point of embedded machine learning is to capture a little bit of the insight and understanding and hard-earned wisdom that an expert has, and distill it into a little model that can then automate that in a very tight, narrow context. So in this factory example, we need somebody to label the data set, saying, is this part correctly manufactured or not? And then the model can help distinguish between those things in the future. And that model can go and run in a context where it wouldn't be viable to have a human expert, because, it's a little tiny camera inside of a machine where it gets really hot, for example. So
Yeah.
that's the whole point of what we're doing here, really.
Great, fantastic. So we talked about distributing intelligence, and I was wondering if you can share with us briefly what you think about how digital twins, which is one of these other high techs or domain that is used these days and is growing and developing. So digital twins and edge AI. So how are they complementary, and where do you see digital twins helping edge AI in its growth?
Yeah, so I just had a really exciting experience going to NVIDIA GTC,
Mhm.
which was in San Jose the other week. And one of the big things there that was on display alongside Edge AI, which had a big role in a lot of the stuff that was presented, were the idea of digital twins and simulation. And I think there's just such a massive role. These two things go together really, really well, because one of the hardest things, like we've just been talking about, is collecting data and labeling data. And doing that from the real world is difficult, time consuming, expensive. A lot of the time, the reason we want to deploy intelligence on device is because it's hard to get data out from the field in the first place. So even collecting data is a challenge. So if you can build a simulation of a situation that's high
Hmm.
enough fidelity, you can then use that simulation to collect data from and then train a model. And you can even deploy your model back into that simulation and check that it works. And then once you go to deploy into the field, there's this thing called the sim to real gap, which is the idea that just because something works in the simulation doesn't mean it's going to actually work in the real world. But in many cases, it can help you get a lot of the way there. So
Hmm.
we have a demo of Edge Impulse at NVIDIA GTC where we showed how we built a simulation. It's like photorealistic simulation of a warehouse with these machines moving around, forklifts, for example, and pallets. And we were able to capture a whole data set in that simulation of pallets and then train a model to recognize and count these pallets. And then that same model could be applied to real video of an actual warehouse. And you can see that it works just as well in the real warehouse as it does in the simulation. So that's a really simple example of how this stuff can work. But if you have a true digital twin, which is basically a kind of synthetic replica of the actual facility or the thing that you're studying, and it's updated in real time with real information, that gives you just even more richness that can
Hmm.
help build your data set and give you more to train models with. So they go together so beautifully. The other part is that embedded machine learning at its heart is a way to capture information about the world and digitize it. And you know, that's something that we've been doing for many years with things like RFID and barcoding, being able to keep track of items moving around a space. I've worked on this my entire career. But now we can actually use sensor data to help understand what's going on in a situation, identify things that are important. And that data can go as signals into a digital twin and help increase the resolution and fidelity of that system that makes it more accurate and a better way to make business decisions. So it all goes together just beautifully.
Yeah, it does. So the industrial metaverse is no longer just a buzzword; it's becoming reality. And yes, you did. I did watch some of the demos at GTC as on the NVIDIA teams, and that was like impressive because I've seen. I think we met like 5 or 6 years ago at a LoRaWAN event in Amsterdam, and it was a time where Zach and you were basically introducing Edge and Pulse, like, and it was created already for some time, but you were really getting into, hey, embedded people, like, you can run ML down there, and
Yeah,
and
it was a public launch party that week. We
yeah,
had a
true. I
karaoke
remember that.
party.
There was like kind of, what are these guys? Oh, wait a second. No, no way. No way. You cannot do that. Well, actually, you can. And the pace at which it's evolving is fascinating. I mean, it's like, unparalleled from my perspective. Like the pace at which the adoption of ML at the edge is going is crazy. And the motivations, you just mentioned digital twins for simulations. There are actual use cases for optimizing processes that justify the investment. And so that's, from my perspective, why it's going so fast. So we want to get into a demo, but I want to have one last myth or reality for you to debunk before we get into that demo, and then we certainly, continue double clicking on that.
Awesome. Let's
So
go.
yeah, yeah. So we're talking about tiny things, right? We're talking about tinyML. We're talking about embedded device constraints and so on. The hype on the other end of the spectrum is foundation models, generative AI, LLM, large language models, right? When should we expect these foundation models, these big things, to be present at the edge? And when I say the edge, I say the tiny edge, right? And coming all the way down to that far end of the systems.
Well, Olivia, funny you should ask about that because I actually just gave a talk about it at the tinyML Foundation's session on generative AI and foundation models at the edge. So
Nice.
um, it's a really exciting topic. We're seeing these incredible capabilities that these models have, and we're also seeing this huge explosion in powerful hardware at the edge. So we're at this, or nearing this inflection point where the generative AI and foundation models are getting more and more efficient, and then the edge hardware is getting more and more capable.
Mhm.
And we're getting to the point where they cross over and we can start running some of these algorithms on the smaller devices. So that's exciting. We're only just getting there. You can do some basic stuff on the edge now, things like signal transformation, denoising, up resolution of things. But long term, I think we will see a lot of these capabilities from these larger models coming down to the edge. So image generation, even like video generation, audio generation. Imagine having like an infinite Walkman that just generates music for you based on your mood. Uh,
Yeah.
all through to the chat GPTs and things like that of the world. But a lot of the capabilities that people are excited about from foundation models aren't even specific things that these models do, but they're broad capabilities that are very, very useful. So I think there are four of these that for me are really exciting. Those are zero shot learning, where you can get a model to do something with that it hasn't been trained to do,
Mhm.
with very, very little extra fine tuning. There's reasoning, which is understanding, making sense of a lot of inputs. There's information retrieval, which is like looking up data and looking up facts and telling people what's going on. And then there's data generation, like creating images and audio and all of that stuff. So there are loads of ways to get those capabilities on the edge without having to deploy a big, massive foundation model to the edge. So that's something I'm really excited about. You can see more about that in my talk.
Yeah, we'll share a link down there so that people can go and check it out. Thanks for
Exactly.
sharing that.
So yeah, as an engineer, I think you've got all these options to bring these capabilities into your products
Mhm.
already. You don't have to wait for the hardware to catch up.
Nice, nice. So another myth and reality to be debunked is that, and we kind of like already teased on that. It's hard. All of that is super hard, right? Optimizing models for devices that constrained is something that is not easy. Well, show us how you do that with Edge Impulse. What's the outcome? We need some demo here.
Yeah, awesome. I'll take you through a very simple demo here on my second screen. So I just want to show something that's using time series data because it's kind of easy to see what's going on. The same flow works the same, works for image data, works for audio, basically anything you can throw at it. But the first stage is always collecting a data set. So you can see here how we have some data samples, and these are accelerometer data, and it's representing a few different gestures. So imagine you have like a wearable device where you can do different gestures to trigger different functionality. In this case, we have wave, up and down, a snake gesture, idle, which is when the device is just sitting there, a fist bump, and a couple of others. And we've collected a small data set. It's only 23 minutes of data that has examples of these different gestures going on. And you can see how the different axes of the accelerometer here show up differently for the wave gesture versus the up down. And so what we're going to be doing is, no magic, no mystery. We're going to be doing some signal processing to extract the pertinent features from this data that help us distinguish between the different types of gesture. And then we'll be training a really simple deep learning model that can do that distinguishing and give you an output. So I collected this data on a little dev board here. One thing that's
Mhm.
really cool about Edge Impulse is that we support dozens and dozens of popular dev boards from all sorts of different silicon vendors out of the box. So chances are you have a device sitting around on your desk that you can just plug in and start collecting data from and deploying models to.
Yeah, yeah.
So that said, we will run on anything, literally anything that has a C++ compiler. So you get accelerated performance on devices that can do acceleration, but broadly, this is super portable. So it's easy to get up and running with one of these supported boards, but if you have a different target, it's not really any obstacle to deployment at all. So once I've collected this data, I can design what we call an impulse. So an impulse is basically a stack of algorithms. So we start out with windowing the data. So this is just like how we're going to cut up the data as it comes in. So
Mhm.
in this case, we're going to look at 2 seconds worth of data at a time. And then we're going to do some signal processing. So we have a whole bunch of different signal processing blocks here that do all sorts of different things. In this case, we're using a spectral analysis block, which is designed by our DSP team to basically pull out a bunch of really pertinent features that are useful for understanding how stationary time series are working.
Yeah.
And
And I just want to bring in a point here. Edge and Pulse documentation is great at explaining what each of these algorithms are doing. So you don't need to be, once again, you don't need to be an expert to understand them. Like if you want to learn about, how you build these neural network and how you end up with, a model that from data, as you were mentioning, using Edge Impulse is a learning process that will extend your understanding of machine learning in general. I think it's a great practical way to learn about machine learning by just doing. And it's a fantastic tool. Once again, like you see, it's all in a website, drag and drop kind of interaction and documentation that really explains what things are about, which once again, it's not about abstracting by creating black box. It's abstracting by providing tools so that people can understand what's going on and how to use them without having all the complexity behind it.
I'm really happy to hear that, Olivier, because that's what we're aiming for. The goal here, it's not just to, create these black boxes that you can't break into and you don't
Mhm.
understand what's going on, but it's just to kind of make that first step easier. But then if you need to go in and do custom things, or if you have your own signal processing expertise, which many companies do, you can very easily plug that in as a box here. So you
Yeah,
can
yeah,
just use it in your system. Same with the machine learning stuff. If you're a machine learning engineer, you can interact with all of this through our Python SDK from a notebook. You don't have to be using our UI. So it really
right.
just fits into the tools that you already have, and you can go as deep or as shallow as you want. Um, so once we've done our spectral analysis, which I can show you here, um, we're doing this breakdown of the signal into different components and providing some statistics about it. And it basically just gives us a bunch of numbers. And those numbers then get fed into machine learning blocks. And we have two of them here. So one of them is a classification block. This is going to help distinguish between the different types of gesture that people are doing. And the other one is an anomaly detection block. So this is a block which is able to understand, does this input look like things that were in the training data, or is it something I haven't seen before? And the key thing there is that if it's something you haven't seen before, then the classification block is just not going to be able to handle it. It won't know what it is. It'll just give you sort of a random output. So you need to be able to know when that kind of situation is occurring. So we use anomaly detection. So if this is an anomaly, if it's something you haven't seen before, then ignore what comes out of the classifier. We just don't know what this is. And it's like we know what it is. We don't know what it is, but we know it's not one of these classes that we care about. So you can actually use anomaly detection by itself as well. So if you wanted to detect, generally when something weird is happening that you haven't seen before, this kind of block will help you there too. So if I go into this classifier, you can see that we have our model here. You can tweak all these different parameters. It's very easy to do if you kind of know what these things are. If you don't know what they are, that's okay as well. We have sensible defaults, and we also have this tool called the Eon Tuner, and the Eon Tuner will automatically explore all of the combinations of different parameters in an efficient way and try and find the best model that fits your target. So if you choose a particular target here and a particular task. So up here we have a particular device chosen. There's a very long list of things that are pre-programmed, or you can do a custom one. Once you've dropped that in, the tuner will automatically try to find models that fit and run well on that device to do the
Wow.
thing that you want. And it will rank them by the performance, and it will rank them by how well they fit on the device. So super powerful. Even if you do know what you're doing, this is a really useful tool because it's so much quicker than going through and trying all the things yourself. So once you have a model, it's very easy to try it out. So if you have a supported dev board like this one, we can just flash some firmware onto the board. If I go to deployment, I click this build button and
Mhm.
it will create a library that contains all of the optimizations necessary for this particular target to get the model to run as fast as possible on that target. So for ARM devices, we're using the SimSysNN and SimSysDSP vector extensions. For more exotic compute, like we have some targets which are neuromorphic compute, so really exotic silicon. We support all of the tooling that creates optimized versions of the model for those devices. Once you've deployed it, you can immediately test. So here on this screen, if I click this button, it'll start sampling, and we can try to do one of these gestures. So let's just do the easy up down one. So now we've grabbed some data, and we'll see how the model performs on that data that was collected live from the device. So here we go. We can see that in our sample, it was a few seconds long. So we did a bunch of different inferences. And for all the inferences, it realized that this was the up down gesture. So you can see it's working there. And we
Wow.
can do another one here if I do something crazy. So let's just do, wild spinning around. This is something that's not in the data set. At least I hope not.
It's gonna be a weird new gesture. Hard to reproduce. That's
Yeah,
gonna trigger. That's gonna bring up your wallet on your watch if you do this. That's what it is.
yeah, exactly. This is the kind of emergency gesture you're probably not going to use much, but we can see that we've detected all of these as anomalies because
Hmm.
it was just kind of crazy.
Oh,
So
okay.
that shows the power of the anomaly detection because if we didn't have the anomaly detection, it would have thought it was the up down gesture because a classification model can't do anything with things it hasn't seen before. But because we have the anomaly detector, it's able to reject that result. And so
Nice,
we know
nice.
not to do whatever we would have done otherwise.
Fascinating. So you've been ingesting data from an actual device, sampling the data. You've been doing some processing, on this data to make it digestible for your models. You've been combining models and algorithms there, compiling all of that, deploying on the device, and it just works. So
Yeah, and
that's
it works quickly too. It works
and
super fast.
yes, it's impressive. Well, I guess the process of fine tuning which model to use and so on, and configuring and so on, can take some trial and error and adjustment, right? Because different sensors, different types of data, different use cases. But at the end of the day, you did all of that in your browser. You did all of that. Well, you were enjoying it because you were smiling when doing it. So it's not something that seems to be cumbersome or hard or whatnot. So I would definitely recommend everyone to go try it out because that's something that is like fantastic to experience and makes to me AI at the edge more real, especially on the tinier edge. And once again, I don't think there's many players out there that deliver that level of programmability, flexibility, as well as fine tuning of everything without having to be an expert on everything. So that's really great. You did a fantastic job at Edge Impulse and it's continuing. I want to ask you before I let you go, because we've been at it for some time now. I know it's fascinating topics. I'm confident people will love and will stay till the end of this recording. But I wanted to ask you, how do you see the next 5 years? Because the last one were crazy. Is the curve of craziness going like that? What are the things that you're foreseeing in the next few years?
Oh yeah, definitely. So I actually have a newsletter where I talk about my speculations about what the future is going to be like. But there are a few trends that I think are really important that are enabled by this type of technology. So we've seen some basic stuff in the demo today, but really everything is coming to the edge. And it's almost, I think, like a law of nature, because there are so many benefits. If you do stuff on the edge, it costs less, right? You don't have to maintain all this server infrastructure. It's more secure, it's more private, which I
Mhm.
find very important. That's one of the most compelling things to me. It unlocks so many use cases that you wouldn't want to do if it involved sending data to the cloud. It needs way less bandwidth. You need way less expensive hardware because you don't need to have networking, or at least you can have low bandwidth networking. And you can do things with really low energy. So if you can do something on the edge, oh, and I missed latency as well. You can do
Yeah.
things with super low latency, super reliable, because the network connection is not going to go down. Another good example of this is self-driving cars, right? All this stuff's so important for them. You couldn't have a self-driving car that's cloud-based, because the internet connection goes down and it's just going to have to stop in the middle of the street. So that
Yeah.
same logic applies to really any kind of interesting thing that you might want to do. So as companies and engineers start to wrap their heads around these capabilities, we're going to see more and more stuff come down to the edge. And it's going to unlock loads of new product capabilities, like things that you can do now with this super low latency, super private machine learning that you couldn't before. It also is going to unlock different business models, because right now we have almost the curse of the subscription business model, where I buy a product that's supposed to be smart. It's an IoT device. So
Mhm.
it's depending on this whole server infrastructure, which the company selling the product has to pay to maintain. So if that company goes out of business, my product stops working. But also, if I stop paying my $20 a month fee, the product stops working. So I think we're going to see a world where we're less constrained by this kind of subscription business model, and companies can build hardware that's really cool and does something really useful and just continues to work in perpetuity, without having to rely on ongoing subscriptions, which is really exciting for people making hardware, I think.
Yeah.
The other big thing is that as the models get more capable, we talked about the generative AI and that type
Mhm.
of stuff, we're going to start to see experiences that no one's even really imagined yet. Like, imagine having a television that generates TV shows. It writes the scripts for you, it generates the video, it creates the music and audio, and you can have a program about whatever you want that you're just sitting and watching. This stuff is coming, right? It's not going to be here tomorrow, but 10 years from now, I would be very surprised if that's not something you can buy. And then consumer robotics. There's been a big challenge where
Yeah.
the robotics hardware, which seems, to be the hard part, it's not the hard part. You can build these amazingly capable humanoid robots that are running around and jumping and doing crazy stuff. But the difficult thing is the software. How do you actually control that body and respond to the environment and do useful things? It turns out you can't just write some simple, if statements to get the robot to fold the laundry. It's an unbelievably difficult problem. And in fact, the the stuff we're doing now, we're talking, trying to sound intelligent, that's way easier to do with a computer than to just control some hands and fold some laundry. So that stuff we found is taking a lot of really intense machine learning, deep learning work.
Mhm.
And we're going to see that on the edge too. So we will reach that point where we start to have robots that have this kind of capability that we've been seeing in the Jetsons on TV decades ago, which is very exciting. And all of that is powered by edge AI. There's no way you could do that in the cloud. You can't
Yeah.
control a dexterous household robot with a remote cloud connection. It's just not going to work. So
Yeah.
huge things are coming. This is a great space to be in. And whether you're on the embedded side or whether you're on the machine learning side, I think this is where all the cool stuff is going to be happening over the next 5-10 years.
Agreed, 200%. I think the IoT crowd we have here totally backs you up on this statement, because we're seeing that all over the place. Like, software on the edge is becoming more and more intelligent thanks to AI, and in all dimensions. And so we're seeing that happening. That's for sure. the timeline to me is what's super interesting. It's like it seems like it's accelerating, and so
Mhm.
we're going there really fast. So that means that I will invite our audience here, if they're not familiar with Edge Impulse, to go try it out, because Edge AI without Edge Impulse, from my perspective, is not happening. Is not happening, at least not as fast and as efficiently and as safely and so on. And so I would definitely recommend everyone to go try it out, at least for learning how things work. Because once you learn it, you'll get back to Edge Impulse because you go try something else and you'll be like, okay, let me like that was working really well, so I'm gonna do that. So I
Yeah,
really
I
appreciate. Yeah.
one thing I'd say is that once you start playing with this stuff, you start seeing applications for it everywhere. It's one of those things where, it's not necessarily intuitive without having some experience, but as soon as you get your hands on it and build a little prototype, you start noticing that there are so many things in our world that could benefit from this little bit of intelligence being applied.
Yes. Yes, and the IoT guy in me is biased and would say that it's you see all these scenarios because there is a tangible physical device, sensors and actuators, and it makes it so much more interesting and fun. And definitely you will leverage Edge AI and the tools like Edge Impulse to give life to these things.
Exactly.
And you don't need to be a data scientist. You don't need to be a super genius to make it happen. You can implement things that are very interesting and very powerful really rapidly. Dan, thanks a lot. There was a lot to unpack today, but it was super interesting. I really appreciate your time. And I look forward to more episodes with you because I will have you back. That's for sure.
Oh, thank you so much, Olivia. It was a real pleasure chatting with you today. And thank you so much to everyone who's been listening. Go and check out Edge Impulse. I'd love to hear what you think.
Thanks. See you all. Bye.
Bye bye.